And we have the mathematical one. And the mathematical one, it is, well, a monad. A monad is just a monoid in the category of endofunctors. Hey, Denise. How's it going?
Cool, just be busy.
Yeah, I can imagine. So welcome. By the way, we're streaming today.
Nice.
Yeah. So yeah, I love my broadsword. Someone in the stream was commenting about the broadsword. I actually on purpose put it there just to show it off. All right, so welcome, Dennis. We were starting with the definition of a monad. We have a more technical one. The technical one is the way in which I personally like to think about it, which is a design pattern for decoupling pure computations from a context of the computation. So, we're gonna work more into it because this is an intuition, and the problem with intuition is that it can be a little bit broad, right? And we also have the mathematical one, which a monad is a monoid in the category of endofunctors. There's actually memes around that. But we're actually gonna see what does that exactly mean. Well, first of all, actually, before approaching the concept of monad, I would like to open this software I have for drawing on my computer right here. I'll put it here and talk about the concept of abstraction, right? So the way in which I would like to very quickly approach it is that sometimes in life we see patterns, right? Like, for example, we see there's maybe a wooden bowl of a wooden bowl, and then you have a glass of maybe of water, whatever, maybe whatever something else, right? And then you realize they all share something in common. Like, for example, in this case, everything is concave, and we like to say, okay, all of these items share something, and that thing they share, we're gonna call it they're all concave objects, right? And then we discover that they do share more things, like properties. In the case of concave things, they all can hold, for example, liquids inside or other items inside. So the power of starting to describe things in nature in a more generic way, which we will call this abstraction in a more abstract way, is that once you're presented with a new object and I tell you, hey, this item is concave, then automatically you gain for free all the rest of the knowledge of things that are concave. In this case, if I tell you, hey, this new item, hey, it is concave, then you automatically know, hey, I can drink water out of this, right? Which is amazing. In this case, monad is one of these type of abstractions. One of these type of abstractions which describes a lot of things. And once I tell you, hey, here, take this object in the programming language, this is just a monad, then you automatically know a lot of things about that object, right? And this is one of the most powerful things about abstractions, especially in functional programming, that it becomes a common language or a common way of communicating things. And this is very powerful because then when we're understanding a new API or sharing a new API, we can use these very abstract descriptions of the thing to share knowledge automatically for free. And these are not just abstractions, but are abstractions based on mathematics. And mathematics is this human activity that for millennia has been developing all of its efforts into trying to describe things in nature, but in in a way in which is as correct as possible, as logical as possible, right? So it is extremely powerful indeed. Uh, so let's see what type of things monad describes. So, for example, um, when we talk about an abstraction, one way in which we can start discovering it is see what all the items which fall into the abstraction have in common. So in this case, for example, um, we have a list, right, of 1, 2, 3. We have a future, um, a future successful of 1. We have what else? We have an option, right? Perfect. An option of 1. What are the things they all have in common?
You can put something in and take it out.
You can, yes, that's a really good one. You can, okay, let's write it here. You can put things into it. What else?
Flat map.
You can flat map them. Flat map the. Okay, you can flat map them. What else?
For us, it's enough here.
For us, it's enough here, but I would like to add that you can also map them, right? And actually, there are a lot of other things they have in common, but I would like to keep these 3 together right now. So, for example, in this case, here, as Jeroen said, I'm able to put things into it. In this case, list, I was able to put 1, 2, 3 into it. In the case of future, I was also able to put 1, and option also put 1 into it, right? Then also we can flat map them, right? But what does that mean? What is your intuition behind flat mapping?
Okay, flat map is some kind of operations that allow you to run operation on top of something in this context and provide as a result other context with some data inside of it.
Okay.
Something like that.
Okay. You want to add something?
No.
No. Okay. Perfect. So so I think this is one of the most core thing about thinking about monads. Flat map, and actually I will say even flatten, which is a flat map, but that does not take one function, but it takes 2 levels of. You can put a list inside a list, right? You can make a list of lists, or an option of option, and you have 2 levels, and you can flatten it, right? Like take them both and squeeze them into only 1 level, right? And this is the signature, or this is the most important thing that all monads have in common, right? But when you flatten things, right? So when you're doing flat map or flatten, what are you essentially doing? What you're essentially doing is combining those 2 containers, level of containers, right? So I wish it was not called flat map, but something related to combine, because a flat map is actually a way to combine 2 monads, so 2 lists or 2 futures or 2 options that will respect the laws within the context itself, right? So what I would like to do is actually stop calling them context and actually start calling them functors, right? So these contextual things are actually functors, and when you think about functors, you should think about context, right? So, for example, and I even go so far to think about it as um, um, paradigms. So you have your normal data, right? Your pure data. So functions that go, like, for example, from integer to string, etc. There's all your types, which are very simple and nice, integer, string, whatever. And then you have these wrappers that actually change a small paradigm into the data. Like, for example, an int can become a list of int, and now the new paradigm is that there is not one value, but there can be several, right, at the same time, all together. Then you wrap it into a future, and suddenly you add the extra paradigm that the value is not yet here, right? It might be in the future. Option, it adds to the optionality, right? It's a whole paradigm, it's a whole small world to understand. Um, and and these functors and these paradigms, when you flat map them, what you're essentially doing is combining these two effects. What does it mean to combine two optional values, right? What does it mean to combine two lists, right? In the case of lists, for example, it means to make the cross product, right? And to have all of the values. In the case of optionality, it means I will only combine them if they're both of them are present, right? If one of them is not, then the result is disappears, right? So let's see actually. So for example, when we take an option and then we flat map it, flat map takes the value which is inside and it requires you to return something else, right? Let's say, for example, we return none. But if we inspect flat map, if we go to the definition of flat map of option, then we see this, right? These are actually the rules of combination for basically what this current option is. So basically this current option is with the one that we created out of this function, right? So we have this, and then we have that, which is the function that we created out of the value in this one. And we return another one of the same type, right? Or of this one. And in this case, option has its own specific rules, right? But what we're essentially gaining is then again a way to combine these two things. Are there any questions up to now? No? Okay, perfect. So what I like to do is to take small pauses because I tend to ramble a lot and I start talking. And in order for you to learn something, and also the viewers in the stream, for you to learn something, it is important for you to also make an actual effort for reflection and thinking, right? What I like to say to people is that we programmers are actually philosophers, because programmers, we're just applied mathematicians, because we take all these abstract objects and we actually do computation with them. But mathematicians are actually just applied philosophers, because they like to describe things in nature, The only other thing that they have is that they actually use logic for it, right? They are very strict about the things they're saying. They want to prove the things. So, as philosophers, what we need to do is reflect and think. And if we're just listening, if you're just watching a video, and if we're just reading an article, whatever, we're not thinking. So we need to think. So the way in which I like to do it is by making some questions, and I'm gonna make one question, and please answer it. Try to write it down, the answer or something, and then we're gonna analyze it, and then from that question, we're gonna do another one. So the question right now, I'm gonna remove this. The question right now is, what is a monad? And please just don't try to go for the definition of the book. Just out of what you before understood about a monad and based on what I just said, please write down what is your own intuition and what do you think a monad is right now. So please write it down, and then after 1 or 2 minutes, we're just gonna review the answers. And then for those 7 people who are viewing the stream, thank you for viewing. It'd be really cool if you can use the chat of the stream or the Discord to also share your own answer. Also, do you want some paper? I don't know if that's better for you. Do you want some paper?
No, this is
Okay. And you, Dennis?
No.
All right. So, do you have something?
I have something. Well, shall I read it out loud?
Yes, please. That'll be awesome.
It's a container type to separate computation from a common pattern that it encapsulates.
Yeah. Okay. Good. So we have what I like about your own definition is the strong emphasis on decoupling, right? Which is something that us programmers we want to do all the time. We want to decouple things. It becomes extremely useful, right, to control code. So Dennis, do you have something?
Okay, let's call it some kind of wrappers that allow you to combine it with other wrappers of the same type, according to some internal laws of this wrapper.
Yeah, perfect. I think that's also like really good. So think I'm gonna write here some of the keywords you said. So the coupling and combination and wrapper and pure computations versus computations inside a context, right? What else? Rules of a context, right? Awesome. We have 2 persons in the stream also adding their stuff. So in functional programming, a monad is a design pattern that allows structuring even complex program logic in a way that is both generic and declarative. Wikipedia for life. Yeah, of course, Kevin. Now it's Kenny. I'm just messing with you. So okay, Kolov, Asen. Asen is actually a really good friend of mine and also a member of Lambda One. So he says something that has the ability to flatten, distinguishing between good and bad outcomes. Okay, it's interesting that he said distinguishing between good and bad outcomes. Is this something that does apply for every type of monad? Is it because I will change it a little bit to um, um, that good and bad outcomes are part of every law or every rule within the context of every monad. Is this really true?
For me, it can be not.
Okay, no. What does your intuition says, Jerome?
I also think it might not always be the case.
Yes. So actually, it's not always the case. So actually, this gives us a really nice next question, um, which is then try to think of a monad that does not involve failure. Do you already have one?
I would say the list, but the list, yeah, it can have 0 elements or more, but none of them is failure, I would say.
Okay. All right.
It. ID.
ID.
Yeah.
ID is a really good one, right? Okay.
But it's existing example, and also you can guess about something that, for example, delayed computation. You have a wrapper that will provide the same result as your lift interior, but after some delay, for example.
Which one again? Sorry.
There is no name for it, but you can simply write it by yourself.
Yeah.
It still can be a monad.
Mm-hmm.
You can leave something into it, you can like flat it,
Mm-hmm.
but there is no bad outcome.
Yeah. All right. Awesome. So that's a good one. Now, what we're gonna do now is we're actually gonna try to write one, like to actually write a monad and these rules of combination, right? So if you get ready to write some code. So yeah, Asen also said list. So yeah, list. List is interesting, right? Because you could take the empty list as some kind of failure, but not necessarily. And then there's also a non-empty list. There's a monad called non-empty list, which is a list that always has elements, and this one is also a monad, right? So we found by counterexample that there are monads which do not involve failure, right? Monads are extremely useful for handling failure, of course, like with the either monad or the option, but it is not something that describes every monad, right? All right. So what I'm gonna do is I'm gonna start writing a monad, actually a pretty useless monad. And then from here, you're actually gonna try to write your own. Asen says, sure, it is not always the case. There are good and bad outcomes, but isn't it the coupling of logic and context, shortcutting the essence of this coupling? But isn't the coupling of logic and context the essence of this coupling? I think I don't completely understand your question, Asen. But I mean, yeah, I mean, if your question is, isn't a failure part of the decoupling for some monads, then yes, that is true, right? Several of them, they involve the notion of failure, but it is not the case at all. Failure is really important for us as software engineers, and that's why sometimes monads become really important for us, right? We can decouple the failure from the loss of our of our program, which is extremely important, right? It's really nice to have one position in which you code the business rules, and then another one in which you code everything else. So that's really cool. So let's write something. So I'm gonna do a monad that prints things in the middle. So um, actually, I'm gonna do a really simple monad. Let's call it case class ID. Okay. And monads are containers, so we must use a type arguments for it. And in this case, ID contains that A. So what is it proper from a monad? A monad has flat map, right? And has pure. Pure, we're gonna put it. Pure is a function that actually, as Jeroen said, brings something from the outside world into the monad, right? So we're gonna put it in the object. So def pure A takes an A and puts it into ID. And that one is really simple, right? Because it's just a constructor function of ID. Then we have flat map, and then again, the type signature of flat map is that you're gonna take the current object, then a function from that goes from whatever the monad has inside to a new one of another type, right? And then it will return it. Well, it's not necessarily gonna return the same one, but it's gonna return something of the same type, right? Now let's try to implement it for ID. ID in this case is what we call the environment monad, or the identity monad. Is basically the monad that wraps every type, but that does nothing to it. So can you think of an implementation for this? Maybe Dennis, probably you know how to do it. No worries, no worries. So, if you thought about it a little bit, then, well, ID is essentially doing not much, right?
Yeah, and there's not much implementations for it.
So we already have A, so that's cool. So the only sensible thing that we can do is apply it to F, right? So we can say F of A, and this returns an ID of B, which is already what we were looking for, right? So the identity monad is not doing much. It's actually just function application, right? So so yeah, so that's basically it. let's do something, one that has some more context, right? Let's do something dumb, like something called printing. So normally we use monads to decouple a context like side effects into decouple it from more pure computations, which is extremely useful, right? Side effects is one of the things that really bite us on the bum later. So let's do monad printing that besides carrying an A, it also carries a side effect. In this case, a function that takes nothing and does nothing. And this is, let's call it side. So I don't know about you, but this type signature actually reflects everything that it is about side effects, right? It is a function that takes nothing and returns nothing. That is the clear type signature of a side effect. Now, what we can do is delay this side effect. So in this case, with printing, we can apply your function to A, and well, these ones are gonna be printing, and what this F is gonna produce a new printing with basically a new side effect. And what we can do with this one is maybe take the old side effect and the new one and compose it into a new side effect. For example, we're gonna create a new function that goes from nothing and that first executes side and then executes result.side. And then we can return a new printing which takes the result.a or b and with the new side effect. And to printing, what we're gonna do is actually make a function that lifts a side effect. Lift side effect, which is gonna take a side effect, so whatever you want here, and returns a printing of A, right? So for that we're gonna need an A, and it requires a value, so we're gonna provide it. So a printing of A and A with side. Oop. Sorry, this needs an equal, so let's do this. Printing A side. We can also make here another function which says add side effect, which takes another side effect, returns a printing of A, and returns a new printing of A, and with the same A and our new side effect, which is the old side plus the new one, right? that's it. This ID of printing can be this one with the side effect that does absolutely nothing, right? Now, are these operations pure? Is add side and leave side and flat map, are they pure? Are they pure functional programming? Let's remember that pure functional programming is defined by functions not having side effects or being referential transparent. Referential transparent is saying, hey, you can substitute in a program the function for its result of its application, and the program will basically not change. Why? Because basically the function did not do any side effects. So are flat map and add side and leave side, are they pure or are they not?
I think size itself is not pure because it returns units, so if it didn't do anything, then it would be...
Yeah, it's pure because we are not calling actually side inside our functions that we defined here.
Yeah, so exactly. So all of these functions are actually pure because we're actually not executing any side effect. We're delaying the side effect. We're actually just making a composition of functions that will execute the side effect. So what we're basically doing is building a program that will generate side effects, but it's actually not executing them. So actually, let's use it. So let's see. Val a, let's do a printing.pure of a, right? And then we can actually say here, hey, let's create some functions that will actually generate some side effects. Let's do, for example, def print. Okay. Now, print is gonna return a new printing of a, and by basically doing printing of a with the alt a, but we're gonna add a side effect. So we already have a function that adds the side effect, this one. So let's use that one. So add side effect of print line a. Okay, this print is still pure because then again, as Dennis said, it is just building a function, but the function itself is a value. So we're just generating a value that later on we can execute, and which will basically open the cache and letting all the side effects execute at once. So here we can say val result equals, and then our famous for comprehension. So let's take a out of printing. So printing a, right? Let's call printing a dot print, right? Let's do something else. What else can we do? Let's transform it. So let's transform a into, so printing dot pure, and we can take a, and then a, sorry, I made some nonsense here. Let's call this hello, and then we're gonna do dot pure a with world, and let's call this b, and then we're gonna do it once more, and then we're gonna put b here, and then maybe bang symbol, and then call print, and then we're gonna yield, let's say, nothing. And then what we're gonna do is first print result, and then do result dot site, and that's a function, so we're gonna call it. So here on the side, we can actually first see, did it already run? Oh, I have some compilation error. B. What does it says? It says value map is not member. Of course, we need to add map. Sorry. So yeah, because the for comprehension in Scala, it is code sugar. So if we are yielding something, it requires map. Map is really simple, right? We've seen it before. It is a function really similar, except it does not return another monad. It's just a pure function that gets into the context. So in this case, we can do a printing of the applied f with a and the old side effect. Let's run this. I think it worked. And yeah, it worked. So print result. So this result is actually a printing of unit, right? Let's result, and this printing is string, right? So when we do print result, is actually printing only the data structure. And the data structure itself is just data, so it is actually pure. It's actually just a value. So we're actually not executing any side effects. So we're still within Pure Land. We're still within our beautiful world of no side effects. But with result.side, when we call it, we basically open the cache to all the side effects. And if you remember, print is the one that adds the side effect that prints the inner value. So in this case, it printed first hello. So actually, oh yeah, it's a line. So first printed hello, because that's what we said. It says printing a.print, which was hello. Then it prints hello world with a bang. Why? Because we added a to world, which was hello, and then we added to b with bang, and then we also executed that one. And it does not print result, because result is only within the monad, but we never compose any side effect that will do anything with it, so it does not appears there. And that's it. So here's another monad. And actually this monad was extremely useful, because what it's helping us is to delay all side effects by basically just composing the functions that does the side effects, combining them all together, and then leaving it to the right moment to execute all the side effects. And this is actually the source for a really common monad called I/O. I/O is slightly more complex, not too much, but it actually basically does that. So, if is there any questions right now?
Well, my guy, I think I typed everything, but it's not printing anything.
All right. I'll help you in a moment, but first I'm gonna leave this question. The Actually, it's gonna be an exercise, which is um, try to implement um, one of these monads. So we have um, eval. Um, eval you can refer to um, type level dot. Let's let me open it. So we have type level cats. Probably several of you already know it. Have data types, and in data types, do they no longer have eval? Yeah, they have eval. So eval basically determines the type of evaluation, and it's actually a monad. So you can take a look and try to implement it, or you can also try to implement try, or you can actually at least implement option, or what other monads do we have? So were you able to solve your issue, Jeroen? Ah, okay, perfect. I wanted to leave the exercise and then help you, but Dennis is awesome. Mm, eval try option. What other nice monads do we have? Either is a monad. So that's actually a bifunctor. So it might include. What else? I'm gonna tell you this. Function one is actually a monad. So you know that all functions actually have their type in Scala. So a function from A to B, it's actually a function. So this type here, over here, and actually when we do Scala allows you to do everything that is a bifunctor, like this one, to do it in fix. So you can do this. So just like either. And then actually function one has a really nice type alias, which is this one, right? So my function one is a monad in the same way that either is. So you can also give it a try. And this one is actually called. Well, we'll see it in a moment. But yeah, try to implement one of these. Yeah, segfault AX. Yeah, either is a good one. Sorry, I didn't see you before. Actually, if any one of you guys want to join the voice chat in Discord, it's also cool. Says I must admit the printing monad you just showed is a good example of the coupling computation with context without having a bad outcome. Yes, exactly, Asen. So the context was, well, side effects, and then your pure computations, well, you have them, right? And then again, we were talking that monads is all about combining things, and in this case we were combining the context by composing the side effects without executing them. So we basically printing is a monad that combines side effects without. You might as well call it reader. Last people won't know. Yeah, indeed. Function one is also well known as a reader monad. You can also find it in cats, but I wouldn't look at the code because that will take you to the concept of Kleisli arrow that we'll actually see in a moment. And also the concept of monad transformers, which we won't see today, but are also interesting. functional programming is all about combination, like really. Uh, Monads is about combining context, and monad transformers is about combining monad. So it is always we try to combine everything. That's what we call algebras. Algebras is actually just the fine art of finding combinators, ways of combining things. I mean, what is the classical algebra we get in school? Is basically that, right? Is trying to combine numbers. That's the algebras we see in school. But as programmers, we actually have a lot of other algebras. In this case, for example, the algebra for combining side effects is this beautiful monad. So if you have any questions or if you're having any complications right now trying to implement a monad, one of the monads you chose, please let me know. Meanwhile, I'm gonna add maybe some more monads here. Let's see, a decoder. Any decoder is a monad, right? So like a JSON decoder, which is basically a decoder is a function from decoding like something you want to decode from, like for example JSON into A. This one is a good one. Free, yeah. You have the free monads, which are also very, very, very interesting, and we can see another day. Free is a good one. What else? There are a lot. Like seriously, once you start seeing and identifying these things, everything is a monad. Everything is a monoid, because actually monads are monoids, but we're gonna see that in the second half. Yeah, pair. So tuples are monads in the same way that either. So a tuple from AB is a monad, but for this to be monads, either or the tuple, you need to fix one of the types. So you can only flat map over maybe one of the types. Okay, we have list. Well, we have the empty list. We have things that are not monads, like for example the validate. That's just an applicative, but we can see that later. How's it going, guys? What monads are you trying to implement? Option. Awesome. And you, Denise? Try. Perfect. You're trying to implement try?
Yeah.
Also in the stream, if you're following and if you're coding yourself, please, if you have any questions, just fire them away. Actually, I would like to add what is the context that is the coupling each one of them. So eval is actually the coupling, the context of when to evaluate an expression. Try is the coupling, the possibility of a throwable or an exception. Option is the coupling, the possibility of a null value or something basically simply not being there. Either is decoupling a certain type of duality of a value, right? Something might be A or B, but not both. Both. How can we? This either and either is actually just a coproduct, and I would like to leave that there, but we can see it in another one. Function one is, I will say that a reader or a function is actually the essence of dependency. So what is a function from A to B, but at B, a B to still to be that is still to be, right? Okay, what is a function from A to C that a C that is still to be, that requires an A in order to be a C, if that makes any sense. What is a decoder? Well, it's a potential A that will come from a JSON, right? So decoding, of course. Free is actually decoupling monad itself. So it is basically it is trying to structure a DSL and bringing this DSL the ability of combination in the same way a monad does, right? So, okay, this one, it requires its own meetup, but let's say that free decouples interpretation. AB decouples, it's basically list of two items. You can see it as a list of two items, and list, you can, some people say that list decouples, how do you say when something is random and not stochastic? It is, I forgot the word. Well, let's say randomness. Because a way of mathematics to handle randomness is by considering all the values at the same time. But yeah, let's leave it simple. And this one is a non-empty list. I said empty list, it's non-empty list. Multiple values. Non-determinism. Yeah, thank you. Yeah, non-determinism is what I want to say. So multiple values or non-determinism. And stochastic is the same. Stochasm. Okay, I know English anymore. So yeah, what else? Multiple values without the possibility of emptiness, right? Now, how are you guys doing?
Yeah, I got stuck a bit. That's why I started non-empty list instead.
Ah. Would you like us to go through the implementation, or do you prefer to have it as an exercise for home?
Actually, I would like to see the option if that's possible.
Yeah, of course.
I got stuck there.
So actually, before we do that, let us ask ourselves, what does it mean to combine two options? So option is a coupling the possibility of something not being there, right? So when you want to combine two things, if in the case of option, we're saying if one of the things is not there, then we're just gonna assume that nothing is in there. Like there's a elimination, right? So if we go to option over here, the implementation is very simple, which says if this one is empty, return none, else return whatever the other thing produces. So let's make an alternative one. So so we have maybe, okay, but let's remember that option is actually implemented using what is called as coproducts or unit types. So it is like either. It is either one or the other. And coproducts or union types, let's call it coproducts, do the same as either, but they can be a little bit more lengthy, right? In this case of maybe, it's two cases. One is the case it's a none. It's a maybe of nothing. And then case class just, let's call this not none, but just so that it doesn't conflict with the current none. Let's call just be the one that actually has a value, right? Let's call this is null. And this is takes an A, extends maybe A, right? And then in maybe we can implement the flat map, which takes a function from A to a maybe B, maybe B, maybe B, and then we say, hey, this maybe, we can do it with pattern matching as well. Is this null? Then just return it's null. And then if it's just an A, then apply that A to the function. Okay? Then again, if this is null, then we don't have an A to apply it to F. So we need to return is null, right? And okay, we will need to use the magic of Scala's covariance for this one. But I can explain covariance in another one. But anyway, if it's null, if this maybe is null, then there's no value to apply to F. So we need to return is null. And if we have an A, then we do have a value to apply to F, right? Which actually segfault is saying that we maybe should demonstrate that that printing is actually a lawful monad. And what a lawful monad means is that so I told you that when we have abstraction, then we're describing a lot of things which share something in common, and therefore we can call them like the name of the abstraction, like convex, right? Everything that is convex, like a glass, we can call it, hey, this glass is convex. Why? Well, because it has certain things that make it convex. Now, when we in functional programming say, hey, is this a monad lawful? Then what it means is that there are certain things that can that actually gives that thing a complete definition of it being a monad. So it is like, well, convex, a thing is only convex if it's shaped, right? Like this, if it has a hole. Then a monad, it's only a monad if there are three laws that are respected, three equalities, three descriptions of the thing, and we're gonna see it in a moment. But I want to finish with this intuition. One thing that I would like to add about monad is that something important. Flat map, it's only able to combine another monad based on the fact that we're building the second monad out of A. Okay? So printing B actually depends on A. We said a function is actually a function is actually the essence of dependency, and in this case printing B depends on an A in order to be printing B. So and that this is actually why option there's only one possible implementation for option. Like we cannot apply F on is null because we don't have an A to apply to it. So maybe is simply we're simply not able to create that maybe B. So in an essence, you can also think of a monad as something that you can chain values or contexts that depend on the previous one in order to be, right? So whenever we flat map any of these, they depend on the previous value to create the next one. So monad it really allows us to chain and put all of these contexts one after the other. That's why sometimes parallelism doesn't really belong to the world of monads, but we can see that later. Are there any questions right now? Does that definition of maybe or option satisfy you?
Yeah.
Do you like it? Is it nice? Does it poke in the nice ways in your brain?
Yeah, it was very it's smaller than I expected.
Yeah, that's the case with functional programming. Sometimes it's actually way simpler than one may think. Anyway, but now for the second part of the meetup, I would like to go a little bit more theoretic, right? And maybe we can hit the laws of a monad if we have time. But what I would really like to expose is its mathematical roots. Okay, I'm gonna put again here monad is a monoid in the category of endofunctors. So let's go one by one. First, we say it's a monoid. Then we say, hey, it has something to do with these categories, and has something to do with this even more funnier word, endofunctors, right? So let's go one by one, right? Let's see what is a monoid, then let's see what is a category, and then let's see what is an endofunctor, and then why all of those words together mean monad, okay? So first, monoid, probably several of you already know, monoid is a way to describe an algebra, right? So we say an algebra, it's always the combination of two things into another thing of the same type, right? So for example, here, this is an algebra, and we're basically saying I can take 1 and take 2, combine them using addition, and it will return another thing of the same type, in this case, integer. We also go through the process of abstraction because we actually find that this is the case for other things. So for example, string concatenation also is some kind of algebra, right? There are a lot of them. but then we start describing them because there are some that have certain properties. The first property that I would like to say is closure. If you see these algebras are all closed, which means the operator is returning something of the same type. So the operator actually looks something like I take an A, I take two A's and return another A. This is the type signature. So this means closure, to be closed, right? And then all algebras which are closed, we call them magmas. Then we have so the fact that for example we can do a1 plus 3 plus 2, and this is gonna be the same as adding first 3 and 2 and then 1, and this is called closed, and this is called associativity. So let's say so A star another A of the same type star another A of the same type. So these are closed. So I'm using types here. Normally mathematicians will do X, Y, Z just to say, hey, these might be different actual values, but I'm just using types here. So A star, right? So this is still closed, and this is associativity. And this is all algebras that are closed are called magmas. All algebras that are closed and associative, they're called semigroups. And finally, all algebras that are closed as associative, and that there's a special element between all those elements of type A, like for example when we do 1 plus 0 equals 1, basically we're saying, hey, A combined with this special element, which is also of type A, will equal the first element, right? Like for example, the empty string with the empty string here will make a string concatenation a monoid. So this is called the zero element, and this is called a monoid. So we're saying, okay, a monad is a monoid, okay? And a monoid is an algebra. Algebra is all about combining things. And what did we say about monads? Monads is all about combining contexts. So we're already cool with that, right? It says this makes sense. Monads is all about combining context, and so it makes sense that it's a monoid, right? Somehow, because it's an algebra. It's combining things. So this is a monoid. Now let's look at category. So what is a category? Category is something even more abstract. And by abstract, whenever we say abstract, we mean more generic. We mean it describes more things. And also you need to use your imagination more, because it becomes less concrete. So let's use our pencil here. A category is first some objects, right? Let's call this one this object. Let's just say, hey, it's A, and this object is gonna be B, and this is gonna be C, and there are not just objects but also mappings between the objects. Let's say A, I can map it to C. So this looks like a function. Let's say that B, you can map it to A. So that's another thing there are in categories, mappings between the objects. Another thing that there are in categories is the ability to compose these arrows. So that means that if there is an arrow from this object to this one, and then another one that will take you to another one, there's another arrow that goes directly. So if this arrow is called F and this one is called G, then this one is gonna be called F composed with G, or F after G. And there's also some special arrows called the identities, which are arrows that basically compose to the same thing, right? And all of this is a category. So we can actually we can think of several things that are categories. The easiest one for ORS programmers is all the types on our programming languages with all the functions in our programming languages actually make a category. It has everything, right? And also I need to say function composition, it's associative, right? So that means that it is the same to compose F with G and then with H. And this is the same as doing it first G with H and then with F, right? So this is everything that we require for something to be a category. The types, so if these objects are types, let's use another color. If this object is a type and this is another type, let's say this is integer and this is a string and this is something else, and these are our functions, like for example, if this one is a string and this one is int, then probably this function here might be something like to string, right? We can transform every integer into a string. And it is indeed a category because functions are composable and they're associative, and there are the special identity function for every single member, which is the identity function. It's really easy to implement. Yeah, Asen is saying, hey, maybe it's better to say morphisms or arrows instead of mappings. Yeah, mapping is an intuition, but probably the correct name is either morphism or arrow, because it's just mathematicians putting another name for it just to say, hey, okay, a mapping is a mapping, a function is a function, but these morphisms can be other things besides functions. Can be, for example, logic entailment, right? When the objects are proofs or logical statements. But yeah. So so this is a category, right? Now, what is a functor? Imagine that we have a category here with its objects and its morphisms and everything. And then we have another category here, because yes, we can have several categories, which are not necessarily this one, right? And we can also have some special morphisms, or if you want the intuition functions or mappings, that will map every single element on this category and every single morphism into this one, right? So this is like another arrow that goes from here to here, and that for this A, it's gonna find another one here called f of A, right? This is just a way of naming this element here. Just say, okay, it's not exactly A, it's f of A, just because this functor is called f. So it's just a way of naming it. And this functor will preserve certain things like the structure, but it can basically mix and match. Now, what does this mean for our programming languages? This means that actually, oops. Let me take blah, 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 blah. Okay. This means that this might be, for example, Scala, this one here, and this one might be option, right? So we can go from integer into an optional integer, right? And this is the case with everything. And then we say that this is the option functor because we're able to go from every single type inside the category Scala to every single type in the category option. And even the functions as well, right? The art of, the ability to bring these functions to this world of options is actually called map, right? Map will help us take these pure functions that go from int to string into a world where we can actually map from an option of int to an option of string, right? Now this is a functor, right? So we say option is a functor. Now, why do we say endofunctor? Well, endofunctor is the same as a functor, except that instead of mapping to another category, it maps to the same category. So it is not very complicated. And sometimes it mixes and matches, sometimes does something. But what we say is that option is actually an endofunctor. Well, why? Because part of the types of Scala, let's say we have, then again I here int, and then we have a string. One valid type in Scala is actually option of int, right? And then the functor option is actually mapping every single one of these types into another type within the same category called Scala or Haskell or whatever you want. And even it goes so far that it can do it for every single type. That means that it can also do it for option of int and map it into an option of option, right? And this goes to the infinite. And you might say Scala is an infinite category because you can have an infinite amount of types, options, and iterate it in options always, right? So option is an endofunctor. And every single functor in Scala is actually an endofunctor because you can annidate them. You can put them inside another one. Okay. So let's go back to our definition. Monad is a monoid in the category of endofunctors, okay? We already saw what is a category, what is a monoid, what is an endofunctor. And now we're gonna mash all of these together. But before that, are there any questions? This is a part of the meetup in which we introduce maybe the mathematics just, to be full. And if we will be rigorous, then everything that I say, we will have to prove it. And it's actually not that hard. But we're not gonna do it because of time. But the important thing here is to get out a preview of the mathematics with a minimum amount of intuition. So it is okay if you don't understand this at the first time. For sure, it took me quite a bit for me to understand all of this. But the important thing here is that this brings us an intuition to work with our programming languages, to deeply understand things, and also in the process, I would say it's really nice and fun. But are there any questions right now? Maybe the stream? Okay. All right. So let's bring all these concepts into the concept of a monad, right? For that, I would like to talk about composition of endofunctors, right? And composition of endofunctors is really simple. I would like to give mostly the intuition. And the intuition is basically saying, hey, if you have a functor, let's say, for example, option, right? An option of A, right? And then you have another functor, like, for example, try. A try of A, right? We said these are endofunctors. So basically this A inside might be another try or another option, right? So we can have the composition of two functors by saying, hey, option composed with try is actually also a type, it's also a function. It's also a functor. So let's say that takes an A. And this is basically equal to just an option, a try inside an option. I don't know about you, but this looks awfully like function composition, right? So I could tell, hey, option and try are functions, and I just change this symbol to composition. That's a really awful symbol of composition. I just change it to composition, and then the definition looks like really similar, right? Like option after try. So first apply A to try and then to option. And actually that's what it is, because a functor looks a lot, it's also a mapping. It's also moving A into the world of tries, and option is moving this whole type, which is try of A, into the world of options. So so this X, we're gonna call it composition of functors, right? Now function composition is actually a monoid, right? Like it's really simple to have so the monoid, a function is a monoid. Let's say we have some function f of type int to string, right? So it's whatever. Then we have g, which is let's say string to something else, like float, whatever, right? Then we can compose them. So val fg equals f compose with g, right? So what is compose doing? Compose is doing, actually, it's combining these two things. It's combining f and g into into f of g. Let's actually add, it's a function, f of g is of the same type. It goes all the way from int to float, right? And okay, I'm gonna do this. It's the integer, and then is f after g, right? G takes a string. Oh, sorry. I'm doing it wrong. So it's first f and then g. So in this case, right? So so what do we have? F is a function, g is a function, and composition is yielding another function. So it is closed, right? Good. Function composition is a magma. Okay, then, is it associative? Well, yes, right? So if we have another h that goes from float to another thing like string again, then it is the same to first compose. Let's so int to float. Let me change this one to to F. And this one to G. So that it goes into string to string to float to string. And this is first G and then F. Well, it doesn't really matter, but yeah. What it says, segfault, it's easier to talk about functions of type A to A, right? They form trivial monoids under composition. Yeah, it is true. It is easier to talk about a function from A to A, but I want to generalize it. Actually, not being too general since I'm using specific types, but this is just to help to the intuition, right? We can generalize it by saying, hey, this is actually a function from A to B, and this is a function from B to C. Right? This still applies. Let's remember that. Let's actually do composition. So composition, it actually takes A, B, and C. It takes a function from A to B and a function from B to C, and returns a function all the way from A to all the way to C, right? And this is very simple. We first get an A, right? Then we first apply it on X, and then on Y. And a function that goes from A to C, A to C, can be A to B, which is G, the composition of G and F, right? And then we can have a third one, def H, which is a composition C, D. This one goes from C to D. And we can have the function GH. What are you saying, default? No, I mean to use functions of type, say, string to string. Then you don't have to make the types line up because they're triply composed. Yeah. I understood you that. That is true, but I would like to show that in function composition the types align, but that still makes a monoid, right? So I don't want to go too trivial. But GH is maybe a function from B to D, right? B to D, by saying is a composition of, I first need to go from B to C through F, right? And then from C to D with H, right? And now we can have everything together, right? FGH. Actually, I'm mixing this a little bit, so it's not in the traditional way. But this is a function that goes all the way from A to D. And this is the composition of, first I have A to C. I have all the way from A to C, so F of G. And then we have C, so we only need to make that extra step that goes to D, which is H. And this works, right? But we had another way of implementing this. right? We had a function that first only makes one simple step from A to B, which is G. And then a function that goes all the way from B to D, which is FH, right? And what is this? This is actually associativity, right? It is the same to first do two and then with another one than do the two last ones and then with the first one. And this is basically what we did. So this is actually the proof of function composition being a semigroup. And finally, for it to be a monoid, we only need the special zero element that will do f composed with the special element is just f, and that's the identity function, right? So it's a function that does absolutely nothing, and if we compose, for example, G, which goes from A to B, compose with the identity function, it's gonna go from B to B and do nothing to B. It's basically just G, right? So identity function is a zero element of the function composition on monoid. So what are they saying? That's good. Fair enough. Okay. It was a sec fault. Was maybe not feeling too good that I didn't use its triviality. But anyway. Now, in the exact same way, functor composition works. All right. These are functions and these are functors over here on the right. And actually, functor composition also works in a very similar way. Like it is the same to, instead of using option and try, I'm gonna use capital letters. So F composed with G, composed with BH, it's the same than first composing G with H and then with F, right? Which basically ends up in a functor that is F, an H inside a G, and 1, 2, and 3 here. An A inside an H, inside a G, inside an F, right? Like a try inside an option, inside a future. Something like this, right? But now, let's make it, and these are all endofunctors, right? Because we said, hey, Scala, all its functors are endofunctors because all of these A's can be other functors, so it's everything goes to the same category, which is your programming language. Any question up to now? All right. So we need to make the actual final step, which is make the category of endofunctors. So I told you, hey, you can make a category of a lot of things, right? And one of the things that you can make is actually of functors. Okay, it goes really abstract. I know category theory goes really abstract, but it is really interesting and it's really cool. So instead of having just types as your elements, we're gonna make one of the objects a functor. Okay, let's. I'm gonna call it big F, right? And then I'm gonna call it here another F, big G, which is another functor, and H, which is another functor, right? H are functors, right? Are mappings between categories or arrows between categories. But now we're gonna make them objects of a category. And the arrows, we're gonna make them something called natural transformations. And natural transformation is something really simple, which is actually just mapping one functor to another one. And in Scala, it's also really, really, really simple. Like, for example, in Scala, we can have a case class, let's call it natural transformation, or actually just this arrow, right? From f to g, just a function, okay, that given an f of a, it transform it and g of a, it transform it into it takes an f of a and transform it into g of a, right? Let's make it this an abstract class or a trait, right? So let's create, for example, a natural transformation from option to list, okay? F is a functor, G is a functor, option is a functor, list is a functor, and we can say, hey, natural transformation of from option, okay, to list. I'm gonna delete this right now. Okay. This is being applied like this, like either, or like function one. And we need to create a new object. So from option to list. And if we implement the methods, we have an option, and we need to get a list of a out of this option. And it's actually extremely simple, right? So if f of a is a none, then we return the empty list. And if there is something in there, we can make a list of only one element. And voila. That's everything that there is to know about natural transformations. It is just a way of transforming one functor into another, right? So in the case of option to list, it's really simple, right? Now let's go back to our category, where the objects are functors, and the arrows or morphisms are natural transformations. Natural transformations can also be composed. Actually, you can prove that this is actually a category by saying, hey, natural transformations can compose, and it's really simple. It's probably very trivial for in the mind to see that if you have a natural transformation that goes from option to list, and then another one that goes from list to something else, then you can just apply first one and then the other one, and voila, right? You have the identity natural transformation, right? Which goes from option to option by then again doing nothing. And then what we can do is create a monoid out of this, right? How? Well, a monoid is closed, right? So in this case, in the same way in which there was a string, an int, and when we were saying, hey, for the monoid of int, we're just gonna work with int because it's closed. Well, in the same way for functors, so let's say this is option or list. In the same way, we're gonna create a monoid by saying, hey, we're just gonna work with option or list. And now let's think about functor composition. Functor composition is actually a natural transformation. Why? Because it goes from one of these functors into another one. So like, for example, option inside of list, right? This is another functor. So So functor composition is actually a natural transformation, right? And we can make a monoid out of this. So if you have, so let's make it first. So our operation is gonna be functor composition. But instead of composing option with list, we're just gonna compose options, right? In this case, right? And this is okay. And now what I'm gonna do is I'm gonna make this to return actually just an option, right? So why? Because we need to be closed. We need to be close. Is if we're combining two options, then I need to get another option back. Functor composition in this case is gonna give us an option inside an option, but we're gonna transform it, okay? How do we transform it? Well, do you remember something about monads that allows us to go from an option inside an option into just an option? Flatten, exactly. So flatten is the monoid operation that makes a monad a monoid, right? And then, do you remember something about a monad that wait, okay? What is the next thing that we need in order for this to be a monoid? We need the zero element. So this is okay. Let's say this is flatten, and then we need the zero element, and the zero element is in this case pure, right? So pure is the one that is going to be our zero element or operation here, and this is going to make a monoid, okay? And actually everything behaves, it all makes sense now. Like monads are just monoids, yeah, because monads is only about combining combining these functors, right? I said that all monads also have map, right? And map is the signature function of a functor, right? So options, lists, they all have map. Why? Because they're functors. And they're also monads. Why? Because we actually can combine them in a monoidical way. So there you go. A monad is actually just a monoid, and for composing these functors, which are actually just contexts. And I think this is just amazing. I mean, this is beautiful, and this is the thing that is going to allow you to identify new monads, right? So whenever you're programming and you see like, hey, I'm doing this thing, which is a completely parallel universe that could be decoupled from my pure computations, and I can map over them. Okay, so it's a functor. Actually, let me give you a tip. If you make something like case class, and then like something, and then you decide to make it polymorphic, say, hey, it requires an A and does something else. The fact that you're putting a type argument here, you're already making it something that can be generalized as an f of A. Probably this is a functor. Actually, I can think of something that is like this and not a functor. Even if you don't use the A inside, you can still map. You can do the functor void has an A but has nothing inside, and then you can actually map, right? with taking a function from a to b and returning a void b, which just, what does it do? Well, it just builds a void of b. Bam, right? And so it is almost everything that you do it in this way is a functor. And then flatten is actually combining these things, and pure is actually the identity, the zero element. You can, which takes us to the monad laws, right? What are the monad laws? Well, they are really similar to the monoid description. So, for example, you have the left identity, which says, hey, flat map followed by, and I'm going super fast now because we're out of time, but flat map and then pure should be the same thing as just doing flat map, right? And that's actually the monoid left identity as well of the zero element. You have the right identity, which is the same thing, right? You do first pure and then flat map, and should be the same thing as just doing flat map. And that's also the right identity of a monoid, 0. They're associative. A monoid needs to be associative, and monads are associative with flatten and flat map. You can check it by yourself. So voila, this is how the world of category theory got completely mapped into our world of programming language, and ended up being a beautiful method of decoupling or side effects and extra context from our pure functions, allowing us to write our business logic on one place, writing side effects on another, decoupling, making our code super nice and secure, and not having to deal with a lot of, for example, option allows you not to do if it's null everywhere, right? It's just amazing. It's really nice. So is there any questions? I know it was, I know this required a lot of mental steam into it, because we had to see everything. Let's recapitulate. We had to see what is a monoid, we had to see what is a category, what is an endofunctor, what is a functor, and all of that. But in the end, everything connected. What is a natural transformation? But in the end, everything connected. Everything finishes in, it's just a monoid or something like this. And this is why functional programming is so powerful. We're able to see through the code of things. Probably people are using monads and they don't know, right? They're using monoids and they don't know. Whenever you're actually summing 1 plus 2, you're actually taking the advantage of a monoid. And now we have a common way of communicating and talking about this. Any question? No?
No, not for me.
Okay, great. Well, then it's already 9, and we're gonna wrap up here and say goodbye to the stream. Thank you, people, for tuning in, and I hope to see you in the next one, next Thursday. And please do join the Discord. We're gonna use this as a main channel of communication. And if you have any questions or you want to collaborate and share something, please just join Discord and ask there everything. And yeah, hope to see you guys next one.
Thank you very much.